Hello, everybody. So this week we're going to be working on Chapter 13, Part 3, Implicit Differentiation, Logarithmic Functions, and Inverse Trigonometric Functions. First of all, we're going to start with implicit differentiation. So what is implicit differentiation? Okay, let's suppose that we have an expression such as x cubed plus y cubed minus 9xy equals 0. Now notice that this is not a function of y in terms of x. So it's not a function in the sense of it won't pass the vertical line test and all that. But we can still do implicit differentiation with this. So what is implicit differentiation? Now notice that you have two y's in this expression. This one is cubed, and this one is to the power of 1, but it's also multiplying 9x. So implicit differentiation is basically the same thing as doing normal derivatives for expressions that are all in terms of x. We will do the same with y, but we will include as well a chain rule with y. So let's take a look at what I'm talking about. So for example, let's start, we do this the same with the power rule, term by term. So the first term would be 3x squared, like we normally do, 3x squared, plus, and first we treat the outside of this expression, y cubed. So we would write 3y squared, but you have to do the chain rule with y. So this would be times derivative of the inside, which would be derivative of y. Now in this next expression, we have a multiplication. So we have to apply the product rule, right? So it would be the first term minus 9x times the derivative of the second term, right? Plus, here we have to be careful with this minus 9. I'm going to factor it out. Maybe it's better like that. So plus the second term times the derivative of the first term. And the derivative of x is simply 1, so we leave it like that. And this equals 0. So once we have this, what we have to do is leave the terms that have y prime on the left-hand side and move everything else to the right-hand side, right? So let's rewrite this for a second here. We can rewrite this as 3x squared plus 3y squared times y prime minus 9xy prime minus 9y. So what we're going to do is that we're going to move the terms that don't have y prime to the right, and I'm going to factor out y prime. So I'm going to be left with y prime times 3y squared minus 9x would be equal to minus 3x squared plus 9y. And then finally, we can send this to divide to the other side. So we're going to get y prime is equal to minus 3x squared plus 9y. And all of this divided by 3y squared minus 9x. And then finally, notice that we can factor out the 3. So this is going to equal minus x squared plus 3y over y squared minus 3x. So this would be the derivative through implicit differentiation of this first expression. Now notice that here we have things in terms of y as well. That's normal. That's normal when you do implicit differentiation. So if you wanted to find the slope of the curve at a given point, you would need both coordinates. You would not be able to do it just with the x coordinate, such as we did before. Okay, so here we are on example 13.4, and it says, consider the equation for the unit circle, x squared plus y squared equals 1, which is a relation, not a function. Letter A, solve for y and write all equations that express y as a function of x. Then find the derivative for each of these functions. Okay, so if we have that x squared plus y squared equals 1, we can rewrite this as y squared equals 1 minus x squared, and therefore y will equal plus minus the square root of 1 minus x squared. So that means that y is either equal to square root of 1 minus x squared, or y is equal to minus square root of 1 minus x squared. So what we're going to do is that we're going to grab these individually and find the derivative. So let's start with this one. So if we grab this expression and we do the derivative, we're going to get that it's going to equal 1/2 times 1 minus x squared to the minus 1/2 times negative 2x. And this is going to equal negative x over the square root of 1 minus x squared. But at the beginning, we said that 1 minus x squared is the same as y, as we can see here. You see that? Therefore, this is going to be minus x over y. Okay, let's do the next one. So the second case. Here the derivative would be equal to 1/2 or minus 1/2 times 1 minus x squared to the minus 1/2 times minus 2x, and this is going to equal x over the square root of 1 minus x squared. But again, notice that if this is true here, it means that this equals negative y. So this would be the same as x over negative y, which is the same as minus x over y. So we get the same answer in both cases. So in part B, they ask us to find the derivative of a unit circle by implicit differentiation. So again, we know that x squared plus y squared equals 1. So let's find the derivative of this by implicit differentiation. So by implicit differentiation, this would be 2x plus 2y times derivative of y is equal to 0. Let's rearrange. So we get 2y times derivative of y is equal to minus 2x. So the derivative would be minus 2x over 2y, and this will be minus x over y, which is the same expression again. And then finally, in part C, they ask us to find the equation of the tangent to the unit circle at point negative 1/2 comma square root of 3/2. Okay, so if we want to find the equation, we're going to need the slope. Now we know that the derivative of the unit circle is minus x over y, so this is going to give us the slope. So at negative 1/2 comma square root of 3/2, the slope of this tangent, which is the same as the derivative, of course, would equal minus 1/2 over square root of 3 over 2, and this is going to equal 1 over square root of 3, which we can rewrite as square root of 3 over 3. Okay, so we have everything we need to find the equation, because the equation would simply be y minus square root of 3 over 2 is equal to square root of 3 over 3 times x minus minus, so x plus 1/2. And then if we multiply and rearrange, we're going to get that y is equal to square root of 3 over 3x plus 2 square root of 3 over 3. And this would be the equation of the tangent at that point. Okay, so now we're in example 13.15, and it says, find the points on the graph of x squared plus 4xy plus 13x squared equals 9 at which the tangent is horizontal. So whenever they talk about tangent, we need to find the derivative. So let's find the derivative of x squared plus 4xy plus 13y squared is equal to 9. Okay, so this is implicit differentiation, right? And I'm going to separate the 4 from the x times y, just in order to be careful there. So we're going to get 2x plus 4 times, it would be the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. And this plus 26y times derivative of the inside, right? So times y prime. And this equals 0 because 9 is a constant. Okay, so at this point we can simplify by dividing everything by 2. So this will be now 2 and this will be 13. So now I'm going to do distributive property just to see what I get. So I got x plus 2xy prime plus 2y plus 13y y prime equals 0. So like I did in the previous case, I'm going to keep this term and this term on the left-hand side. So I'm going to factor out the y prime. Y prime times 2x plus 13y is going to equal minus x minus 2y. Therefore, the derivative is going to equal minus x minus 2y divided by 2x plus 13y. Very well, but they want us to find where the tangent is horizontal. When you have a horizontal line, the slope is equal to 0. So really, they want us to find where this equals 0. Now, because the denominator cannot be 0, in reality, we have to find out where minus x minus 2y is equal to 0. So we have to solve for y here. So we're going to get minus 2y is equal to x. Therefore, y is equal to minus x halves. Okay, but there's an infinite amount of points that could make this equation true. But we're interested in the case that we're dealing with now, right? So that means that we have to plug this back in here. We have to plug it back in there, substituting y, and then we can solve for x. That's what we're going to do next. I'm going to get rid of this, and we will do that. Okay, so let's rewrite this. We have x squared plus 4xy plus 13y squared equals 9. And we found that the tangents that are horizontal would be in the form of y equals minus x half. So we said let's substitute with this in there. So once we do that, we're going to get x squared plus 4x times minus x halves plus 13 times minus x half squared equals 9. So this implies that we're going to get x squared minus 2x squared plus 13/4 x squared equals 9. Okay, so now let's multiply everything by 4, just to get rid of this here. So we multiply everything by 4. This is going to be 4x squared minus 8x squared plus 13x squared equals 36. So if we add like terms, we're going to get 9x squared equals 36. That means that x squared equals 4. So obviously this has two solutions, x equals 2 and x equals negative 2. So these two would be the points at which you have a horizontal tangent, or at least the x-coordinates, but I need to find the y-coordinates. To find the y-coordinates, I will have to plug them in here, right? In there. So let's do that. If I plug that in there, I'm going to get the two coordinates, or the 2 points at which the graph has a horizontal tangent. And that's going to be 2 comma negative 1 and negative 2 comma 1. Very well, so now we are on part B, where it says determine whether each point is a maximum, a minimum, or neither. Okay, so in order to find out whether a point is a maximum or a minimum, I'm going to use the second derivative to do a concavity test. So remember that the second derivative will equal the derivative of the first derivative, right? So we really need to find the derivative of the expression that we found before, which was this over 2x plus 13y. Okay, so the derivative of this will be the second derivative of the original function. And let's remember that here we have to do the low d high minus high d low over low squared thing. So this would be low 2x plus 13y. We always start with the denominator times the numerator, or the derivative of the numerator. So this would be minus 1 minus 2 y prime minus x minus 2y, high d low now, right? So this times the derivative of the bottom function, that would be 2 plus 13y prime, and all of this over low squared. So low squared is going to be 2x plus 13y, and this squared. All right, so now we have this expression. We don't want to expand it. Instead, we're going to leave it like that, and then we're going to plug in the points. Recall that the points that we found, where the slope is 0, therefore whether you have a maximum or a minimum, were 2 comma negative 1 and negative 2 comma 1. But we can't plug those in yet because we still have this y prime expression. But that is the same as the derivative, so we're going to substitute this with the first derivative, right, with this expression here. So what we get is a much longer expression that goes like this: 2x plus 13y times minus 1 minus 2 times the whole expression. And this minus x minus 2y times 2 plus 13y prime, but instead of y prime again, we write the first derivative. And all of this, of course, over 2x plus 13y squared. Okay, so now let's do a concavity test. So what we plug in is the x coordinate, of course, right? So for 2 comma negative 1, we're going to get that the second derivative, which is this that we found here, the second derivative is going to give you guys, if you test it out, 81 over 125, which is a positive value, and because it's greater than 0, it means that the concavity is upwards. So that means that this point here is a minimum on the graph. Likewise, if we do the other coordinate, negative 2 comma 1, and we plug it into the second derivative that we found before, we're going to get a negative number, which is minus 3 over 343. And because this is negative, it means that the concavity is downwards at that point. Therefore, this is a maximum. All right, so the next topic we have to deal with is derivatives of logarithmic functions. And the first one we're going to take a look at is at y equals natural logarithm of x. So the question is, how do we find the derivative of this? Okay, notice that the inverse function of this is e to the y equals x. Now these are the same thing basically, right? E to the y equals x. So if we want to do the derivative of this, let's apply the derivative to both sides of the equation. So derivative of e to the y equals derivative of x. Okay, so the derivative of e to the y is e to the y, but applying the chain rule, we have to multiply times the derivative of y. And the derivative of x is just 1. So that means that the derivative will equal 1 over e to the y. But we already said that e to the y equals x. So this equals 1 over x. In other words, the derivative of natural logarithm of x is 1 over x. Okay, now that this is the case when we have a natural logarithm. But what happens in the case of a different base for logarithmic functions? So let's separate this here for a second. And let's suppose we have an expression like log base b of x. We can do a change of base. Remember that this is the same as saying natural logarithm of x over natural logarithm of b. So let's apply the derivatives to both sides of this. So the derivative of log base b of x is equal to 1 over natural logarithm of b, this is a constant, times the derivative of natural logarithm of x. But this is equal to log base b of x, derivative of that should then equal 1 over natural logarithm of b times the derivative of this, which is 1 over x. So we can conclude that the derivative of a logarithm of base b, or any base, would then equal 1 over x times the natural logarithm of whatever that base is. Okay, so now we are on example 13.6, part A, and it says, given g of x equals 1 plus x over 1 minus x, find the first derivative. Okay, so that if we have that g of x equals 1 plus x over 1 minus x, then the derivative will be, remember, low d high minus high d low over low squared. So this would be then 1 minus x times 1 minus 1 plus x times negative 1, and all of this over 1 minus x squared. And then if we simplify this, now we're expanded, we get 1 minus x plus 1 plus x. And all of this over 1 minus x squared. And then if we simplify this, we're going to get that this and this cancel out. So 2 over 1 minus x squared. Okay, so for part B, they say, hence, find the derivative of f of x for f of x equals natural logarithm of 1 plus x over 1 minus x. Now notice that this is the same expression from before. That's why they have the word hence, because we need to apply what we got before in this case, right? So if f of x is the natural logarithm of 1 plus x over 1 minus x, then the derivative of that is going to equal 1 over this expression, 1 plus x over 1 minus x. And applying the chain rule, I have to multiply this by the derivative of the inside of this expression here, which we found was 2 over 1 minus x squared. Okay, so then, because this is a reciprocal, we're going to get that this is the same as 1 minus x over 1 plus x. times 2 over 1 minus x squared. Okay, now here this is going to cancel out with one of these, and then we have a difference of squares here. So this is going to give us 2 over 1 minus x squared. So this would be the derivative of f of x. Okay, so now we are on part C, and it says show that f of x is 1, an odd function. So let's start with that. It's an odd function. Now from the last practice, if you guys recall, you had to do a proof. And the proof you did was that if you have a function, say f of x, if f of x is odd, then its derivative is even. So if we can prove this, it will automatically imply that. Okay, so let's recall what the derivative was, right? The derivative, let's write over here, the derivative we found was equal to 2 over 1 minus x squared. So what we have to prove is that this is even. In other words, that f prime of minus x should equal f prime of x. And this is obviously true because 2 divided by 1 minus x squared is definitely going to give us 2 over 1 minus x squared. Therefore, the derivative is even. Hence, f of x is odd. For part 2, they ask us to show that f of x has no stationary points. What that means is that it has no maximum and no minimum. Remember that to find maximums and minimums, we have to equal the derivative to 0. So what happens when we equal 2 over 1 minus x squared to 0? Well, this has no solutions. Therefore, since this cannot equal 0, the function f has no stationary points. Okay, so now I'm going to get rid of this to work on part 3, which says that f of x has one point of inflection, and we have to give its coordinates. So for part 3, we will need to do the second derivative of f of x, right? So the second derivative of f of x is going to be the derivative of the first derivative, right? So derivative of the first derivative, 2 over 1 minus x squared. And this is just the quotient rule again. If you do it, it's going to give you 4x over 1 minus x squared squared. So if there are inflection points, it occurs where this equals 0. But this has a solution, right? The solution would be x equals 0. So there should be an inflection point at x equals 0. Now, an inflection point means a change in concavity. So in order to verify that this actually has a change in concavity, we are going to have to test values that are before 0 and after 0 to see if there is a change in concavity. So let's take negative 1/2 and plug it into the second derivative. If you do that, you're going to get negative 32/9, and this is obviously less than 0. Now something after 0, let's prove a value like 1/2, and if you do that, it's going to give you positive 32/9, which is greater than 0. Therefore, we can conclude that this is a point of inflection because of the change in concavity. The coordinates of the point of inflection would be then 0 for x, but the original function was f of x is equal to natural logarithm of 1 plus x over 1 minus x, right? So if we plug in 0, we're going to get natural logarithm of 1. But natural logarithm of 1 is 0. Therefore, the inflection point is at 0, 0. Okay, guys, so now we are on example 13.7, and it says find the equation of the tangent to the graph of y equals log base 10 of x to the 3 at the point when x equals 4. Express the equation exactly with any logarithms being expressed as natural logarithms. Okay, so if we have y equals log base 10 of x to the 3, then the derivative will equal 1 over x to the 3 natural logarithm of 10 times, doing the chain rule, the derivative of the inside, right? So that would be 3x squared. And if we simplify this, it's going to equal 3 over x natural logarithm of 10. So this is the derivative, and that's what we need to find the slope. So when x equals 4, the slope of the tangent is going to equal 3 over 4 natural logarithm of 10. Okay, so we have the slope, we need the points. So we know that x is 4, therefore we need to find the y coordinate. So when x is 4, let's plug in 4 here, we're going to get that y would equal log base 10 of 4 to the 3, which equals log base 10 of 64. But they want us to express everything as natural logarithms, so we need to do a change of base. So this would be the same as natural logarithm of 64 over natural logarithm of 10. So that's going to be the y coordinate. Let me write it over here. So this is going to be natural logarithm of 64 over natural logarithm of 10. Okay, so let's erase this here in order to make room for the equation of the tangent. So we have y minus natural logarithm of 64 over natural logarithm of 10 is equal to the slope. So 3 over 4 natural logarithm of 10 times x minus 4. And then if we expand and rearrange, we're going to get an expression that is equal to this. Y equals 3 over 4 natural logarithm of 10 times x, the slope, plus negative 3 plus natural logarithm of 64 divided by natural logarithm of 10. So this would be the equation of the tangent expressed exactly and with only natural logarithms. Okay, guys, so here we are now with derivatives of inverse trigonometric functions. Now remember that the inverse trigonometric functions are, for example, y equals arc sine of x. So this is the inverse trigonometric function for sine. Recall that this is the same as inverse sine of x, right? Okay, so if we have this expression, this is the same as saying that sine of y is equal to x. So let's do the derivative of these two sides. So if we do a derivative of sine of y equals derivative of x. Now, because we are deriving with respect to x, we have to use the chain rule, right? So this would be cosine of y times the derivative of y is equal to 1. Therefore, dy over dx, or the derivative of y, is equal to 1 over cosine of y. Okay, but the derivative of y, that means that we're doing the derivative of the arc sine, right? But the thing with this is that it's in terms of y, so we have to change it somehow into terms of x. Now notice that sine of y is equal to x, so I would rather change this to an expression that has sine instead of cosine. Now remember that we have the trigonometric identity known as the Pythagorean, right? Which is cosine squared of y plus sine squared of y is equal to 1. Therefore, cosine of y is equal to the square root of 1 minus sine squared of y. So that means that this is the same as 1 over the square root of 1 minus sine squared of y. But like I said, sine of y is x, so we can rewrite this as 1 over the square root of 1 minus x squared. So this would be the derivative. This would be the derivative of arc sine of x. Okay, so here to the left, we can see the derivatives of the other inverse trigonometric functions. And we're going to work on example 13.8, where they ask us to find the derivative of each equation. So let's start with letter A. So in letter A, they want us to find the derivative of y equals inverse cosine of e to the 2x. Okay, so let's remember that for this case, we're going to have to use the chain rule. So we know what the derivative of the inverse cosine is, since we have it right here to the left. So this is going to be equal to 1 over, oh, this is negative though, 1 over square root of 1 minus x squared. But in this case, x squared is going to be e to the power of 2x. So this to the power of 2x squared times, we have to do the chain rule, the derivative of the inside, this expression here. So that is going to be e to the 2x times 2. Therefore, the derivative would then equal negative 2 e to the 2x over square root of 1 minus e to the 4x. Okay, so we're going to work on part B. And for B, we have that y is equal to x times arc sine of 2x plus 1/2 square root of 1 minus 4x squared. So the derivative of this would be, let's see, notice that here, for this, we will need to do the product rule. So it's the first factor times the derivative of the second factor. So this would be then derivative of arc sine, which is 1 over square root of 1 minus x squared normally, but in this case 2x squared times 2, because I have to do the chain rule, so this times 2, plus the second term, or the second factor, arc sine of 2x times the derivative of the first term, but the derivative of the first term is 1. Then this plus the derivative of this term here, for which we do the normal power rule and the chain rule. So this is going to be 1/4 square root of 1 minus 4x squared to the negative 1/2 times negative 8x, which is the inside, the derivative of this here. Okay, so let's multiply and see what we get. So the derivative is going to equal 2x over over square root of 1 minus 4x squared plus arc sine of 2x plus, let's see what we get here, negative 2x over square root of 1 minus 4x squared. So look at these two terms, they can cancel out. Therefore, we can conclude that the derivative of the expression for part B is going to be arc sine of 2x. And finally, we're going to work on part C, which is the derivative of this expression. Now, here we have to be careful because we will be doing chain rule, right? So the derivative of natural logarithm is 1 over x. In this case, it's going to be 1 over x plus y. This times the derivative of the inside, the derivative of this. That's just going to be 1 plus y prime. And this is going to equal then the derivative of arctangent, which is 1 over 1 plus x squared, but in this case, x over y squared times, remember, chain rule, x over y, the derivative of that. So we will have to do the quotient rule. So remember, it's going to be the denominator times derivative of the numerator minus numerator times derivative of the denominator over the denominator squared. Okay, so now let's multiply this and see what we get. We're going to get here 1 plus y prime over x plus y equals y minus x y prime over, so notice that if we multiply y squared times 1, we get y squared. If we multiply y squared times x squared over y squared, we get x squared. All right, so next we're going to cross multiply. We'll do that here. Cross multiply. So we're going to get 1 plus y prime times x squared plus y squared times, or equals, sorry, x plus y times y minus x y prime. Okay, so now this over here, we continue over there, is going to give us x squared plus y squared plus y prime, and I'm not going to expand this because I'm going to have to factor out later anyway, so let's just leave it as y prime times x squared plus y squared, and this equals, and I'm going to straighten this out, and this equals xy plus y squared minus y prime times multiplying by x, so x squared plus xy. Okay, and the reason I'm not expanding this or this is that I would have to factor it out anyway. So let's bring this to the left-hand side and move the other terms to the right-hand side. So we're going to get y prime x squared plus y squared plus y prime x squared plus xy equals xy plus y squared minus x squared minus y squared. So notice that this and this will cancel out. Okay, so now let's factor out y prime. So this is going to be y prime times x squared plus y squared from the first term plus x squared plus xy from the second term. And this will equal xy minus x squared. Then we can add this and this, right? But we'll just rewrite it as y prime is equal to xy minus x squared over 2x squared plus y squared plus xy. Very well, so here we are now on example 13.19, and it says, a painting that is 175 centimeters from top to bottom is hanging on the wall of a gallery, such that its base is 225 centimeters above the eye level of an observer. How far from the wall should the observer stand so that the angle subtended at his eye by the painting is a maximum? So what's the maximum possible value for alpha? We don't need to find alpha, but we need to find x, right? So in other words, how large should x be so that alpha has its maximum possible value? Okay, so in other words, we need to relate these angles here and somehow relate the angles to x. So the first thing we're going to do is translate this into meters. Notice that we have a right triangle here, so we can probably play around with some tangent functions, right? Okay, so in meters, we're going to have two triangles. One that is going to have a length of 4 meters, and the other one that is going to have a length here on this side of 2.25 meters. But for convenience, we're going to write this as 9/4 meters. Okay, so notice that we can relate alpha to theta and beta because alpha is equal to theta minus beta. So how can we put this and this in terms of x? Very simple. We know that tangent of theta is going to equal 4 over x, right? Because this is theta, the larger angle. We also know that tangent of beta will equal 2.25, so 9/4 over x. And then, because this has to be in terms of theta and beta equaling something, right? So theta is going to be the inverse tangent, right? So the arc tangent of 4 over x, and then beta is going to equal the arc tangent of 9/4 over x. So that means that alpha is equal to the arc tangent of 4 over x minus the arc tangent of 9/4 over x. Since we need to find the maximum, we will have to do the derivative of this and equal it to 0. Okay, so let's do the derivative. So the derivative of alpha in terms of x is going to be the derivative of this expression minus the derivative of this expression. So arctangent, remember the derivative of that is 1 over 1 plus x squared. So in this case, 1 over 1 plus 4 over x squared times the derivative of the inside. We have to do the chain rule. Now notice that this is the same as 4 times x to the minus 1. So it's going to be minus 4 over x squared. So this minus something similar, 1 over 1 plus 9/4 over x squared times negative 9/4 over x squared. Okay, then if we multiply this, we're going to get negative 4 over x squared, right? That's x squared times 1 plus 16, 4 squared, because x squared and x squared cancel out. Minus minus, so now plus 9/4 over x squared plus x squared times x squared will cancel out, but we're going to be left with 81 over 16. Okay, so we want to simplify this a little bit. And if we multiply it by 16, we multiply this by 16 and this by 16, we would get, let's see, we get rid of this, and we would get on top was 9/4, so it's going to end up being 4 times 9, so 36, 36, and here we would need a 16. Okay. Whoops. Okay, so now we need to equal this to 0 and solve for x to see if we can get a maximum. So let's equal this to 0. Okay. In order to do that, we would have to cross multiply. So we're going to get minus 4 times 6x squared plus 81 plus 36 times x squared plus 16. We would also have to do the denominator, but we're not interested in the denominator because we're going to equal this to 0. And the numerator is the only part of a quotient that can equal 0. So solving for this, multiplying and everything, you're going to get negative 28x squared plus 252. So this equal to 0. If we do x squared equals minus 252 over minus 28, we're going to get that x squared is equal to 9. Okay, so this has two solutions, right? It has a solution that is x equals negative 3 and x equals 3. But because we're talking about distance, but let's test some values that are before 3 and after 3 in order to verify that this is actually a maximum. So at x equals 2, you're going to get that the derivative will equal 7 over 145. So this is greater than 0, obviously. So that means that the slope of the graph is going up. So the slope of the graph for this expression right here for alpha would be going up. What happens at x equals 4? X equals 4 is obviously after 3. So what's happening to the graph after 3? For x equals 4, you're going to see that if you plug that into the derivative, you will get a negative expression, minus 49 over 2696, which is negative. Therefore, the graph is going down. So that implies then that at x equals 3, we have a maximum for alpha.